Hello, my name is Dylan Womble. I'm going to be going over my contributions to the AStar and PRIMS algorithm creation group with a GUI and animation. That's our project. My contributions were the implementation of the AStar algorithm, the implementation of the linked list priority queue, and then creating the unit tests associated with all elements of the group, all elements of the project. I also did a lot of work integrating both priority queues with the both algorithms, AStar and PRIMS. I'm going to prove out AStar using nodes 0 to 7. These are the same nodes we go through in the report and give you currently detail about why this path is correct. It gives you this current path. I'm going to switch up the path now to show it updates. And then I'm going to run using linked list. I ran that was min heap before. I'm going to go back and show the same. You get the same implementation, same result for running whichever priority queue you want to use. Okay, I'm going to exit out of that. Again, a lot more detail in the report on how that's the correct path. I'm going to go to the AStar algorithm. AStar algorithm is a implementation of Dijkstra's algorithm where we add on a heuristic to improve the performance. The heuristic we chose is Euclidean distance. Essentially, right here we create an H list which is all the H scores for every node in the graph, and then for that index which corresponds to that node ID, we calculate the Euclidean distance between that node and the end node, and we populate that list. That gives you the H score. So the AStar algorithm encompasses the F score, G score, and H score. F score is the G score plus the H score. The H score is that Euclidean distance, and the G score is just simply for that node is the path of adding up the edge weights to get to that node. So AStar algorithm gets the couple inputs: the graph in an adjacency matrix format, starting ID node, ending ID node, and then a min heap boolean to determine which implementation. If it's true, does min heap. If it's false, does linked list. So we do a lot of initialization here. We push the starting node with an F score of 0 because it doesn't cost anything to get to the start node, guaranteeing that that's the first one to be popped off. We initialize some maps that provide us O of 1 access to a lot of this data we're going to need to do our algorithm. Some more creating the H list, some more initializations. We start the algorithm. So while the priority queue is not empty, we continue. If it ever gets empty, we haven't found our distance, we break and we break. So neighbor count is just go through the is just a count going through the neighbors. So we start off by popping the top of the priority queue. That should give us the lowest F score on the priority queue. If that's the ending node, we break, we're done, we found the end node, we found the shortest path. If not, we take that current node we just found, we find all its neighbors. If that node has a weight of greater than 0, meaning that that node has an edge that goes to that node, another node, we continue. We calculate the G score based on what we currently have for that current node inside this map, and then we add the weight to get to the new neighbor node. That gives us the node for the neighbor. If that is not currently in the G score, or the cost is less than what's currently in the G score, we update everything in the maps to say we found a better path. This is the path we want to store for better use. And then we push that onto the priority queue for it to be when it's popped off, when it gets to that point, that we will investigate that node, and then we increment the counter. So this will go through until it finds the shortest path, and then this will reconstruct the path. This is a quick algorithm using the node came from a dictionary to reconstruct the path, and it will put out a list of the nodes it took to take that path. So I also implemented the priority queue. This is simple. We have priority queue node, which uses the F score. That's the F score that we use to sort it. We have the constructors for both. We have is empty to determine if it's empty. Simple implementation. We have a push. So when we add something to the queue, we make sure we find its proper place, add it there, repair the pointers. Pop, we take the top of the queue and then repair the pointers for use later in the AStar algorithm. I'm going to run the unit test cases I did to prove out that those are currently working and that we pass all our tests that we should. Oh, we got an okay. We ran all 5 tests. All of them passed. So we're good there. Um, Again, a lot more detail in our report under AStar algorithm, but this is a kind of a quick implementation about our quick rundown of what I did to support this project. And if you have any questions, please reach out to me. Thank you so much for your time, and thank you for the awesome class.